multiple representation. For instance, it can have two different voltages corresponding to these logical values, or two different types of magnetization, different direction or different helicity. And then you have to manipulate that information. You have to apply, you process this, you apply gate operations. For instance, for a single bit, a typical gate operation is the NOT operation, which turns 0 into 1 and 1 into 0. Every computer requires, in addition to single qubit operations, also 2 qubit operations. That's required for conditional statements like if, then, or while, and so on, and of course for addition or whatever. So a typical operation in Boolean logic is the AND operation, which takes 2 input bits, turns it into 1 output bit, and that output is 1 is both input bits are 1 and 0 otherwise. Now this is an important operation because, as I briefly mentioned before, it loses information. You have 2 input bits, 1 output bit, so you lose 1 bit of information. That means you create entropy. And entropy at finite temperature means heat dissipation. And I don't want to capture the screen. It's not from my computer, that must be from the projector. Thank you. So, because you lose 1 bit of information, it means you have to dissipate K Boltzmann times T, roughly, forget about the ln2, amount of energy. And that's this horizontal line which I indicated to you. And this is not possible to beat if you use Boolean logic. Now, I told you classical information is, for instance, 2 different voltages, and now we come to the quantum version of that. In a quantum mechanical computer, instead of using 2 different voltages, you represent the bit by 2 different quantum mechanical states. For instance, spin up and spin down, or 2 different orbitals in an atom. And the main difference now between the classical and the quantum computer is that in the quantum computer, you can also have superpositions of these states. The classical computer is always either 0 or 1. In the quantum computer, you can have arbitrary superpositions. So you have something like a Schrödinger cat. And of course, for a bit or a quantum bit, you have one specific physical system which has exactly a 2-dimensional Hilbert space. That's a spin 1/2. So spin 1/2 is essentially a natural qubit, natural quantum bit, but you can embed such a 2-dimensional Hilbert space, of course, also in the normal infinite-dimensional Hilbert spaces like a hydrogen atom. So there are many different ways of choosing the quantum system. Now, when you have your qubits and you want to build a quantum computer, you need a bit more than that. First of all, you need as many qubits as possible, say n, and together they form the quantum register. Now, before you can do a computation, you have to store some information in that quantum register. So you have to initialize it, for instance, with the number to be factorized, and the rest of the qubits, maybe you enter 0. And then you do the processing, the logical operations, and these logical operations in a quantum computer correspond to unitary transformations driven by some Hamiltonian, H1 for the first step, H2 for the second step, and so on. So that transfers the input into the output, and at the end, you have to extract the classical information that you want from the quantum state. Why is that necessary? Well, what you get here is a superposition state of many computational basis states. And we humans cannot understand quantum information directly. What we need is a number, for instance, 17, or we need an answer, yes or no. And so that's exactly what this readout step does here. You're not asking me, I suppose. Okay. Now, the power of a quantum computer then depends really on the size of the quantum register and the logical operations that you apply they must be driven by some external control fields, which are typically classical fields. A typical quantum computer may be an array of ions in a trap, and those you represent the total quantum state of these ions you represent by some quantum state psi, and when you do the logical operation, you transform this input state into an output state. And again, I repeat, this is unitary transformation, and of course a unitary transformation by definition is reversible. Being reversible means that there is no information lost, and that means that there is no inherent dissipation in a quantum computer. So this lower level of dissipation, K Boltzmann times T, that we had in the classical case, is no longer present in a quantum computer. Again, you have to drive this unitary transformation by some Hamiltonian, which is in general time dependent, and of course you have to integrate that over time, but for simplicity you can also represent that by an effective static Hamiltonian with, which acts over a certain time t, which would then be the duration of the gate operation. Okay, so that's the basics how you do quantum information, and again you need some logical operations like the NOT gate. That's also important in quantum computers, which again inverts the logical states. For instance, it flips a spin, and that's the representation of that gate operation. It corresponds to a rotation around the x-axis. And general 1-qubit operations can be represented by rotations on the Bloch sphere in the computational basis state of the single qubit. Again, you need also 2-qubit operations, which are conditional operations, and they have typically a control qubit, which is not changed during the operation, but it determines the action that's taken on the target qubit, on the second one. So for instance, in the control NOT operation, the target qubit is not changed when the control qubit is 0, but it's flipped if the control qubit is 1. The main difference to the classical case is that here, again, you have 2 input qubits, 2 output qubits, and so no dissipation. But these 2 operations, C0 plus arbitrary rotations of single qubits, is enough to build a universal quantum computer, a computer which can solve any computationally accessible problem. And this was the basis which was used for the first implementations. I mentioned that nuclear magnetic resonance was the first one which was actually demonstrated. The second one which became available are trapped ions. This is a string of trapped ions. Each of these colored balls is one trapped ion. And then other systems became available like photons. Photons are very nice qubits. They're cheap, they're easy to detect. They also have their problems. And superconducting resonators are one of those systems which have advanced most rapidly over the last few years. And there are more like defects in solid, quantum dots, electrons on helium, molecular magnets. I think there are very few physical systems which have not been proposed for quantum computing. Now, again, let's come back to this experimental test. This was the test with a classical computer, and of course you can perform the same test with a quantum computer, now based on nuclear magnetic resonance. And these are different size quantum registers, and you see that the scaling of the execution time is much more benign than with the classical computer. If you can extend the number of spins that you control, it will definitely be possible to compute with more than 23 spins, and you don't need the age of the universe to wait for the result. Still, this is a limited size, but you can get to larger systems, and I show you one example here. This is a quantum simulation, so it's a simulation of a quantum mechanical system. It's about localization, so it's sort of similar to an Anderson type model, where we actually wanted to see how information spreads in a coupled network. And you see the size of the system grows here roughly exponentially with duration, and the end here is with around 7,000 qubits. This is not a universal quantum computer, but at least for some problems you see you can simulate relatively large quantum mechanical systems. If you want to do something like that on a classical computer, it would take you a few years. Okay, this was existing implementations. Let me briefly mention a few proposed ones. A very famous one is that by Bruce Kane, who suggested to use nuclear spins of phosphorus-31 embedded into a silicon matrix and controlled by nanometer-sized gates which apply electrical fields. I like this system quite a lot, which was also on my title slide. These are endohedral fullerenes. I'm sure these type of molecules are very well known in Mexico. They're called soccer molecules sometimes, soccer ball molecules. And they allow you to store an atom inside, for instance, a nitrogen or a phosphorus atom. Nitrogen or phosphorus atoms are useful qubits, but they're hard to handle without the cage around it. Anyway, so we have a number of promising systems, but I assume most of us are still using classical computers. I'm doing this presentation from a classical computer. So why is that? Well, first of all, most tasks are no faster on a quantum computer than on a classical computer. For instance, a slide presentation will not become faster, fortunately, on a quantum computer. The second point is that it's still hard to make large-scale systems. And the third one, which I'm going to discuss in a little bit more detail, are that the larger the system gets, the more it is susceptible to errors and decoherence. Decoherence meaning that it's losing its quantum properties and becomes classical, and therefore the advantage over classical computers. So where do these errors come from? There are basically two types of errors. One is the error which the experimentalist introduces. Sorry, we're not perfect. And of course, not only we are not perfect, but the machines that we use. We apply control fields, electrical, magnetic fields, and these fields always have a finite precision. If you set your voltage to 100 volts, you never get exactly 100 volts, you get maybe 99.9 volt or 100.01. And this is, don't look at the company logo. This is a commercial quantum computer, which is standing in my lab. It's built by a German-French company, which just opened a representation in Mexico. And it's an NMR spectrometer. And of course, you create these control fields here and you apply them to the sample which sits inside this magnet. Now, the second reason for these imperfections is that it's never possible to completely isolate a quantum system from its environment. You can try, and you should try to do that as far as possible, but for instance, nobody knows how to shield gravity. That is usually not the most important part, but you have, for instance, magnetic fields from power supplies and whatever. They create perturbations of the quantum system which you cannot control and which cause decay of coherence, and so your ideal quantum bit turns into a non-ideal quantum bit. Now, these are the main problems for building larger systems also. And for some time it was thought that it will be impossible to build arbitrarily sized quantum computers which can compute with arbitrary precision. This was fortunately shown to be not true by the so-called threshold theorem, which was proved by two different groups who showed that if the precision of a single gate operation is high enough, you can use error correction to get rid of these unwanted interferences. And this means then that the main focus should be to create high precision gate operations at first. And for that purpose, you have to do a number of things. You have to try to shield your system from the environment, but you also have to design the gate operation in such a way that the finite experimental precision that you have available does not cause too much of errors. And then you have to use error correction schemes. Furthermore, if you look at Hilbert space, it's like a lab space in a way. It's not homogeneous. There are regions in Hilbert space which suffer a lot from the environmental perturbations, and there are other parts of Hilbert space where you can preserve the information for a longer time. And of course, you should try to use that part as much as possible. And then there are active protection schemes which allow you even to suppress the effect of the environmental noise, even if you cannot avoid it. I have a number of options here available, and don't think that it is sufficient to use one of them. If you want to build a useful quantum computer, you certainly have to use all those options. Let me start with one of them. That's the passive protection measures. That's the quiet regions on Hilbert space. And I would like to illustrate the principle on a simple examples. There are so-called clock transitions. If you look at the definition of the second, this is given in terms of oscillation periods of the hyperfine transitions of cesium-133. Now, that is the splitting between the F = 3 and the F = 4 sublevel of the electronic ground state. And of course, these sublevels, they split in the presence of a magnetic field. But two states are not affected by the magnetic fields. That's the MF = 0 states of both hyperfine sublevels. And so if you build a clock based on cesium-133, you will always use this specific transition because it does not suffer from magnetic field noise, which you never can avoid in an actual lab. So that's why this is called a clock transition, and every atomic clock uses such a type of transition which is not shifted by magnetic fields. Now, clock transition consists of two levels, so it's exactly enough to store one quantum bit. And of course, for a quantum register, you want to have more than one quantum bit, and so there is a generalization of that concept, so-called decoherence-free subspaces, which allow you to store more than one quantum bit. So that's for the passive protection scheme. Now let's come to the active measure. The goal is to get back your ideal qubit and avoid the effect of the interference from the environment. And in the case of active measures, what you do is that you apply some control operations which modulate the interaction between the quantum system and this noisy environment. And they modulate it in such a way that you can eliminate the interaction or the effect of the interaction to some degree, and the result will be that you again have long-lived coherence or long-lived quantum information. This is important for quantum computing, but also for a number of other fields like spectroscopy or sensing. Now, this is actually a principle which was discovered in magnetic resonance in the 1950s, soon after the first nuclear magnetic resonance experiments. The idea is the following. You have an excitation which creates the coherence, so that's the storage of the quantum information in the qubit. And because of these interactions, the coherence decays. What you do then is you apply a so-called refocusing pulse, which is essentially an inversion pulse, and it brings back this information. You see, that's a publication of spin echoes from 1950 by Erwin Hahn. The idea is the following, that this destructive interference comes because the individual spins have different precession frequencies. And you cannot change their precession frequency, but you can cause them to trace back their precession. And so if you invert them with this pulse, they go back, and after you wait the same amount of time as between the excitation and refocusing. They come back into phase and you get the echo. So now, this was discovered in NMR. It was applied to many other fields. You have so-called photon echoes, which are exactly the same principle. And that can be applied to any qubit in a dephasing environment. So we've tested that in a qubit system. This is a molecule called adamantane. The qubits are these green balls, which are carbon-13 nuclear spins. And they have an environment consisting of the gray balls, which are protons. And there is a dephasing interaction when you create the coherence, and what you observe is this so-called free induction decay. Now, you can apply a Hahn echo, or you can apply a refocusing pulse, you get an echo. And now we measure the amplitude of this echo as a function of time between the excitation and the observed echo. And what you get is this dashed curve. Yes, the information survives longer than in the free induction decay, but frankly, it's a bit disappointing. It's maybe a factor of two or three longer, and that's not really worth it. So the question is, why does it still decay? Supposedly, the refocusing pulse should bring the dephasing back. Now the problem is, sorry, it's already over. The problem is that the environment here is not static. There are interactions between these protons, and what they do is basically two protons flip their orientation simultaneously, and that means the carbons do not see a static environment, and therefore their precession frequency changes. And when you're trying to call it back, that causes a decay. Now the solution to that problem is also known. That was proposed, that you just have to make sure that the refocusing is quickly enough. So during the excitation or between the excitation and the refocusing, the environment does not change. So basically the spacing between the pulses has to be short compared to the correlation time of the environment. And when you do that, you just can apply more than one pulses if you want to preserve it for a longer time. That was proposed by Carr and Purcell in 1954, and what you get is a series of spin echoes, or photon echoes, or whatever. And yeah, and the important point is that the pulse separation must be shorter than the correlation time of the environment. You can try that in this nuclear spin system. You have the free induction decay and the Hahn echo now on a logarithmic scale, and you see that if you reduce the spacing between the pulses, the survival time of the information gets longer by several orders of magnitude now. These are just a few examples. You can plot now the survival time as a function of the delay between the pulses, and as you reduce that delay, you see that you can increase the relaxation time by roughly 3 orders of magnitude. So not a factor of 2 now, but a factor of 1,000. Then it becomes useful. And applying more pulses obviously helps. Now, maybe you would expect that this curve continues like that. Unfortunately, it doesn't. It saturates and even decays a little bit. There's one other problem with this. All these data were taken with one specific initial condition, namely the spins. These were nuclear spins again. They were aligned with the direction of the rotation axis around which you do apply the refocusing pulse. I call this longitudinal initial condition. Of course, that's what you do when you want to preserve a specific state. But in the case of quantum information, if you know what the state is, why do you want to apply refocusing? It's much smarter just to write it down on a piece of paper, and then you can preserve it as long as you want. So normally in quantum information, you don't know what the state of the system is, or you want to preserve arbitrary states. And specifically, in addition to the longitudinal initial condition, you should look at the transverse initial condition, where the spins are perpendicular to the orientation of the rotation axis. And in this case, the dephasing time does not get longer, it gets shorter. So applying more pulses hurts under this condition. So why is that? Well, basically it's a matter of pulse imperfections. I'll show you that in a minute. And that means that if you want to do experimental quantum information processing, you have to take these imperfections into account and try to reduce their effect. That's the context of dynamical decoupling. Dynamical decoupling basically applies such sequence of inversion pulses, and the problem is you need many such pulses, thousands of pulses. And if a single pulse has a small imperfection and these imperfections add, you destroy your information rather than preserving it. And typical imperfections are finite strength, finite duration, flip angle errors, that's the deviation between 99.9 volt and 100 volts. Maybe you don't hit the offset exactly, or you can't hit it exactly. And in some cases, we see effects of imperfections, although we don't know where they come from. What you have to try then is to make your gate operations robust. Robust means that their performance is close to perfect, even if the control fields themselves, if the apparatus that you use is not perfect. So the effect of the errors should not accumulate. This principle has been, again, discovered in nuclear magnetic resonance. Sorry to repeat that. The idea of the first application of that principle was that you wanted to have a robust inversion pulse. This is a radio frequency pulse. You switch it on for a certain duration, and it should invert the spins, so bring them from the Z axis to the minus Z axis. But because of amplitude errors, maybe they don't get all the way to the minus Z axis. But you can improve that if you basically insert a refocusing pulses into that pi pulse. So you split the two halves of the pi pulse, insert a refocusing pulse in between that, which essentially eliminates the inhomogeneity in the rotating frame, and in the end you're close to the south pole again. So you can use that and replace all the pulses in a dynamical decoupling sequence by such robust pulses. That reduces a lot the effect of gate flip angle errors. Now, this was the very first so-called composite pulse that I showed you. There are better ones around. One of the best that we found consists of 5 pi pulses with different phases or orientations of the rotation axis in the XY plane. It's very good at eliminating pulse imperfections. It achieves the same dynamical decoupling performance in the sense that it suppresses the interaction with the environment. And it has one disadvantage, because you replace a single pi pulse by 5 pi pulses. It means you deposit 5 times as much energy in the system. And for some systems, that's not what you want. Now, you can actually eliminate that problem quite easily. If you just replace individual pi pulse and the delay tau by a composite pi pulse and delay tau, that's not very efficient. What you should do is you split these 5 pi pulses and you have shorter delays between them. That improves the decoupling performance and decreases the power deposition in the system. And then you can further extend that. You have basically a composite X pulse. You combine it with a composite Y pulse, and that gives a very effective sequence, as I will show you in a moment. It's a so-called robust sequence. It performs almost flawlessly, even if you have significant errors in the control field. Let me illustrate that. The horizontal axis here, I plot the flip angle error. So that's the deviation between the field that you apply theoretically and the one which is generated in the lab. Of course, if you have no flip angle error, then the traditional sequences like CPMG perform perfectly. You have a so-called fidelity 1. If you have a flip angle error, in this case of 5%, the fidelity goes to 0. Why? Well, this is the fidelity after 20 pulses. If you have a 5% error, and you accumulate that over 20 pulses, you have 100% error. That's why the fidelity goes to 0. Now we use the same imperfect fields, but we use a robust sequence like the so-called XY4 sequence or this KDD sequence which I showed you, and you see that the fidelity stays very close to 1, even if your error is, say, 10% in the case of XY4 or 30% in the case of KDD. So that's what I call a robust sequence. It eliminates experimental imperfections. Now, this was one experimental imperfection. Of course, in reality, you have more than one experimental imperfection. So here I assume you have a flip angle error and an offset. This traditional CPMG sequence has a, say, usable performance in this green range. This is a color coding of the fidelity, and that's essentially 0 error, and then it stops being useful. If you use this XY4 sequence, obviously you can extend this region significantly, and with KDD you feel almost the whole area here is, say, a few thousand times bigger than in the case of this CPMG sequence. And with that type of dynamical decoupling, you can increase the storage time a lot. For instance, if without any dynamical decoupling, you lose your information in a few hundred microseconds, you can preserve it with these robust sequences for many milliseconds. So what we have here, we store quantum information. That's what's called a quantum memory. It's a quantum state that we preserve for as long as possible. Now, what we would like to do is, of course, not only quantum memories, we would like to do quantum computing. And for that, you have to apply gate operations, and there comes a problem. The dynamical decoupling is designed to eliminate interactions with the environment. But the gate operation, they are controlled by external fields, so that's also a type of environment. And the qubits don't know what type of environment you want to preserve and what you want to eliminate. So if you just try to apply dynamical decoupling during quantum information processing, you will stop the processing. And so you have to adjust the control fields in such a way, and I'm not going into detail, so that this destructive interference is eliminated. I'll give you just the result, and for that I would like to introduce a nice system for doing such experiments. That's a diamond, and inside that diamond, well, you know, diamond is a lattice of carbon atoms, and you will find some defects. That's a so-called NV defect or nitrogen vacancy defect, where one of the carbons is replaced by nitrogen, and adjacent to it is a vacancy, a missing carbon. And it's negatively charged, the one that you normally use, and that gives you a luminescence. You can measure that luminescence as a function of position, and you see some bright spots, and each of these bright spots is a single spin, a single electronic and nuclear spin. Why do we know it's a single one? I mean, obviously it has a finite extent of a few hundred nanometers, and the microscope is not able to focus farther down. You can measure that by doing so-called anti-bunching experiments. You measure the probability of detecting a photon at a certain time after having detected one already. If it's a single center, that probability goes to 0. Why? Well, if a single center emits a photon, it's obviously in the ground state at that moment, and it cannot emit a second photon. It takes some time until it has absorbed another photon that it can emit, and that time is on the order of a few tens of nanoseconds. So if you see such a curve, you know it's a single center. So we're doing now such experiments on a single electron together with a nuclear spin. This electron has a spin of 1, so you have 3 spin substates, and in the absence of a magnetic field, you have a zero field splitting between the ms equals 0 state and the ms equal plus and minus 1 state, which has a splitting of 2.87 gigahertz. And you can measure that splitting by applying a microwave field which saturates the transition. If you do that, you should see a single line at 2.87 gigahertz. In some cases, you see an additional 2 lines. Like in this case, we have actually 2 centers here. This is one slightly out of focus. This was in the focus. And the splitting of 125 megahertz is because one of the neighboring carbons, actually one of these 3 carbons, is a carbon 13. And you have a hyperfine interaction between this nuclear spin 1/2 and the electron spin. And if you measure the free induction decay of this electron spin, you will typically see a pattern like this. If you do a Fourier transform, you see some splittings. You see actually 2 types of splittings in this case. One is because of the nitrogen 14 nuclear spin, which has a spin 1, and one is because of the carbon nuclear spin, which has spin 1/2. Or, okay. So in this type of system, we have tested this dynamical decoupling, these protected gate operations. If you do just the gate operation itself, you lose the information over a time scale of about 100 nanoseconds. And if you do protection, in this case with an XY4 sequence, you can extend the lifetime of the information by at least 2 orders of magnitude. Or you can use better sequences with more pulses, and you get almost 3 orders of magnitude extension. Okay, this, what I showed you before, was just for a single electron spin. If you have a larger spin system, like neighboring carbons, and you use the nitrogen 14, you get more complicated spectra, which mean, of course, that you have a larger quantum register. In this case, we measure the spectrum, which from the electron spin, that's the electron spin spectrum, which has splitting of 8 megahertz because of one adjacent carbon, 5.8 megahertz because of second adjacent carbon, 2.2 megahertz because of the nitrogen 14, and a third carbon, which is splitting of 0.4 megahertz. And so you can use both resources, the electron spin and the nuclear spin, to build more complicated quantum registers. Here, for instance, we have a 2-qubit system, and you can apply various gate operations. You can transfer information from one to the other, and you can measure the coherence and beating of different Bell states, for instance. So you have a large playground for doing that. Now I just noticed that I've already spoken for an hour, and I was told that it should be about, yeah? Mm-hmm.
How do you avoid the NH center? Because you always have a population with a hydrogen atom there.
No, there's no hydrogen.
No. So you...
Why should there be hydrogen?
Because when you have the NV center,
yes,
you always have statistically percentage of the population who have trapped a proton there, which is an NH center.
We've never seen.
It's not desirable for this kind of application.
Okay, I don't know. We've never seen one.
All right.
So maybe, and you mean real in the bulk of?
Oh, yes.
Okay. Mm-hmm. Okay. No, we've never seen one.
Well, that's the problem they have for these spin detectors that are building.
Okay.
In a lattice artificially.
Yes. Mm-hmm.
Implanting the color centers.
Yeah.
But they cannot get rid of the hydrogen.
Okay. I mean, a number of those protons are just on the surface of the diamond. But these experiments are done with relatively deep centers. Maybe that's the reason. But thanks you for the tip. So, yeah, I was told that 1 hour is about the maximum. So I would probably. Okay. Okay, thanks. So let me then continue. But one of the things when you have such a what I call hybrid system, you have different types of qubits. One is an electron qubit, electron spin. The other is a nuclear spin. This has some advantages. It has some problems. The main difference between these types of qubits is that the interaction strength differs by 3 orders of magnitude. That's the channel magnetic ratio of the 2 spins. So, for instance, a typical Rabi frequency, when you apply a microwave field to the electron spin, you get Rabi frequency on the order of 10 megahertz. and you apply a radio frequency field which drives the nuclear spin, you have a Rabi frequency of 10 kilohertz. So that means you have to synchronize, for instance, the gate operations quite well, and not only the Rabi frequencies are different, but also the dephasing times. The electron spin dephases on time scale of microseconds, and the nuclear spin on a time scale of milliseconds. So by the time you have applied your gate operation to the nuclear spin, your electron spin has dephased and you have lost the information. And that becomes important when you're trying to do 2-qubit gate operations in such a system. For instance, you want to apply a control NOT operation where the control qubit is the electron spin and the target qubit is a nuclear spin. So you have to drive it with the nuclear spin Rabi frequency, which means it takes milliseconds, while the information of the electron spin should be preserved. Now, I'll just briefly show how to do that. To do such an experiment, you first have to polarize the spin system. You do that by a laser pulse. You need a second laser pulse to read out the result. And then use microwave pulses, which should be selective for the excitation depending on the state that you want to create, and they may have to be selective for detection. And in between you apply some dynamical decoupling sequence, which I have reduced here to 2 refocusing pulses. And then you apply the radio frequency pulses that drive the nuclear spin controlled by the electron spin. Now, in a normal 2-qubit gate, this would be a continuous radio frequency pulse. To remove the effect of these dynamical decoupling pulses, you have to change these, the type of pulses that you use in such a way that they basically apply the toggling frame. I'm afraid this becomes a bit technical, so we can discuss that maybe at the end. I'll just show you the result. This is a protected controlled NOT operation, and the effect of that is if you do not use this protection scheme, you lose the information over a time scale of microseconds. If you use the protection scheme, you have an almost perfect gate operation which can last up to milliseconds. So this is the typical type of application where you want to protect your quantum gate operations. Dynamical decoupling or these decoherence-free subspaces, clock transitions, so on, they all help to reduce the dephasing, the decoherence of the system. However, you never can eliminate that completely. And so you need, as I mentioned before already, an additional ingredient, and that's quantum error correction. Quantum error correction cannot only slow down the loss of quantum information, it can recover it. So if you apply a gate operation and you have an unwanted additional operation, which is an error, you lose the information along the way, and you can eliminate that by doing quantum error correction. And the basic idea is similar to classical error correction. Classical error correction schemes, they encode the information that you want to protect in additional bits, and you do the same thing in the case of quantum information processing. It's just a bit more difficult for 2 reasons, basically. First of all, quantum information is more valuable in the sense that you can compute more effectively, but it's also more fragile. And you know that from Schrödinger's cat. I mean, who has seen a Schrödinger cat so far? Well, I predict you won't see one. And the reason is basically that while it should in principle be possible to create coherent superposition of a dead and alive cat, that superposition would decay much more rapidly than you can generate it. So complex quantum systems decohere rapidly. And the second reason is the so-called no-cloning theorem. That states that it's impossible to exactly duplicate unknown quantum information. So in a classical error correction scheme, you duplicate the information, you run the multiple copies through your algorithm, and in the end you compare them. In quantum computing, you cannot duplicate your information, and so you cannot directly apply these classical error correction schemes. And the third problem is that error correction schemes usually assume that you can detect the information. So when you compare the two copies, you detect them and you see there is a difference or there is no difference. Again, you cannot do that in a quantum computer because a quantum measurement collapses the quantum state, it destroys the coherence, and so you cannot undo that. So what you do in quantum error correction, you again encode your information in additional so-called ancilla qubits. So to encode a single input qubit, you use, for instance, 5 qubits, where 4 of them, these ancilla qubits, are initially in a state 0. You encode your information in a more complex state, and then you can again apply gate. Well, let's start with the simplest case. You just want to preserve the information. So there may be an error. Then you have to undo this encoding, and then you apply an error correction state. And at the end, you get, hopefully, the information that you put in again in the first qubit. This is so-called perfect error correction algorithm because it can detect and eliminate all possible single qubit errors. So if any of those qubits suffers an error, you can recover it in this state. And you need at least 5 qubits to do that. Again, this was a quantum memory. It preserved the input state, but of course you would also like to do quantum computing, so you have an additional step, a gate operation which you have to put in here, and then you can check if the result is what you wanted. For that purpose, use so-called process tomography. You generate a number of possible input states, you measure the output and determine the operation. You decompose the actual operation into elementary operations. That's the unit operation, a rotation around the x-axis, the y-axis, and the z-axis. And so you can determine what operation you actually did, and you can compare that with the theoretical operation, and you know how good the actual operation was. I mentioned you need at least 5 qubits. Why is that? Well, you need to detect the possible outcomes of such an operation. And if you have 5 qubits, you can have, in the ideal case, you have the no operation which preserves the input state, or you have a single qubit error on one of the 5 qubits, and you have 3 different possible single qubit errors, so you have 15 possible errors, which gives you 16 possible outcomes. And in the 5 qubit system, you have 4 qubits to detect the error. 4 qubits gives you 2 to the 4 possible measurements, and that allows you to detect these 16 possible outcomes. So you can use this detection scheme and perform error correction, and then you can apply the errors. I mean, you want to be sure that you can correct the errors, so you do apply them in a controlled way and then eliminate them. And then you measure the fidelity for each possible error condition, which would be no error, a bit flip, or a phase flip, or a combination of bit flip and phase flip. So these are the 16 possible error conditions. And you see we get fidelities on the order of 90%, which is of course much better than what you expect without error correction, but it's not yet the threshold that you need to reach for scalable quantum error correction. So this was the case for the quantum memory, where the operation that you want to achieve is the identity. And then you do the same, of course, for actual operations like the NOT operation or the Hadamard gate, which is an important quantum gate operation, and you get similar results. Again, test all the different error conditions, and you get fidelities on the order of 90%. Okay. So maybe I'll just briefly mention this. So far, I concentrated on quantum computing using spins. And I mentioned in the introduction that photons are very nice qubits. Why? Well, they are cheap. You get them in any amount you want. It's easy to detect single photons, and their decoherence time is very long. So why is not everybody using photons for quantum computing? Well, there are two problems essentially. One is it's not so easy to have interactions between photons, and you need interactions for 2-qubit operations. Second reason is, well, you can't just grab a photon and do experiments on it. They tend to fly away. So if you want to do experiments with them, you have to keep them in the lab. And one possibility is you store them, for instance, in solid, in a crystal, by absorbing them. So you can have two different electronic states, and you have a photon which is resonant with the transition between these two states. And if it's absorbed, then it's information. It's information. The quantum bit is stored in the electronic excitation of the crystal. Now, electronic excitations tend to decay relatively quickly, and so one possibility to store them for a longer time is to transfer the electronic excitation into a coherence of a nuclear spin. We do that with rare earth ions, which have a non-vanishing nuclear spin, and that allows you to store them for milliseconds to seconds. And actually, a few weeks ago, a paper from an Australian New Zealand group came out where they stored the quantum information for several hours in such a system. That's amazing. So a quantum memory with hours of storage time. We're not that far, but I'll show you the principle anyway. So first of all, for storing them in the electronic excitation, you can extend the storage time to some degree by applying photon echoes. So you apply a laser pulse which refocuses it, and then you can measure the decoherence time. That's on the order of 9 microseconds in this case. So you have not completely arrested, but still in that time it would have flown away for 2.8 kilometers. And then you transfer this. That's what's the experiment I showed you with a single refocusing pulse on the electronic transition. And then you can transfer it by using additional laser pulses into the spin storage, and you reach storage time of the order of 100 microseconds. Then you can apply further protection schemes on the nuclear spin like dynamical decoupling, and you get in the region of milliseconds. This is just a summary of the results here. This is the free induction decay in the electronic transition. You see it decays on the time scale of microseconds. Notice this is a logarithmic time scale. So with the Hahn echo, you can extend, that's now Hahn echo on the nuclear spins, and the CPMG sequence, you can extend it further. And then you can also use these passive protection schemes, which I mentioned, that you store it in a quiet region of Hilbert space. In this specific system, you first have to create this quiet region by applying an appropriate magnetic field. And if you compare now the shortest and the longest time scale, this is an increase in the storage time of 5 orders of magnitude, which I think tends to become useful. Okay, so I think I should really come to the end now, and but I would like to mention a few things, not so much scientific ones, but maybe initiate a discussion here. Why don't we have quantum computers available yet? Well, I would say we have them. I mentioned one type of quantum computers which you can buy. That's nuclear magnetic resonance or electron spin resonance, whatever you like. Then there's a commercially available type of quantum computer which the Canadian company D-Wave offers you if you have a few millions of spare cash available. And there are quantum devices for quantum communication. There's about 10 companies now which offer quantum key distribution systems for optical communication. Now, still, I've stressed the potential of quantum computers. And one has to be always a bit careful. You have heard the same about many systems. Gallium arsenide is just one example. It was often said that it's the material of the future, but that it will always remain the material of the future. I mean, we're still using silicon for most applications. And of course, you see the similarity between the two sentences. So maybe quantum computers will also remain the application of the future. But you can also rephrase it. Will quantum computers be useful? Will it work? Well, I don't think that quantum computers will replace classical computers. As I mentioned, at least so far, there are not that many applications where quantum computers actually are better than classical computers. But you have to remember that normally applications follow the available techniques. And this is let me first mention that quantum computers are useful for a number of applications that we already have, like quantum simulations. And we should also not forget that classical computers have their scaling problems because of the energy requirements, as I mentioned, for instance. So quantum effects tend to become more important. So what we learn from building quantum computers should become important for classical computers also. And the third, which is maybe the most important answer, comes from Krömer. In case you don't know Krömer, he was a semiconductor scientist, and he got the Nobel Prize for semiconductor heterostructures. Now, when he got the Nobel Prize, he told a story that when he was working for a commercial company and he proposed to the management to build semiconductor heterostructure. And the management says, well, no, you shouldn't do that because there is no application of semiconductor heterostructures. Now, semiconductor heterostructures are, of course, the basis for semiconductor lasers, laser diodes, photodiodes, whatever. And of course, semiconductor lasers are now a multi-billion application. So definitely, this manager did not see an application which we know once the material is available. And similar statements about the future were made in a number of cases. This is a famous one. All possible inventions have already been made. That's not very recent. That was said in 1899. And by somebody who definitely should know about inventions. Or this device is absolutely useless for us. That was in 1876 by a telecommunication company or communication company. Thomas Watson about computers. I think there's a world market for about 5 computers. Of course, these were different type of computers at that point. Nobody wants to have a computer at your home. I mean, you know, today, of course, every washing machine is a computer. Again, this was the chairman of a technology company who was no longer producing computers. There are also correct statements, like a computer will weigh less than, let's say, maybe less than 1.5 tons. This was a journalist, basically. Again, a statement which we won't probably subscribe to anymore. And I mean, 640 kilobytes. Of course, a watch today has more memory than that. This is an interesting statement because about the internet, it will soon go spectrally supernova, which is true. And in 1996, it will catastrophically collapse. Fortunately, it didn't. The person who made that statement, again from a company which definitely was interested in that, he at least remembered that. And in English, there is a statement to eat your words. And he did that. So he, or no application for communication satellites. as the head of the Federal Communications Commission. Television won't be able to hold on to any market capture after the first 6 months because people will get tired of staring on a plywood box every night. Of course, we don't stare at plywood box anymore. They're now made of plastic. Anyway, so this was just a few sort of concluding remarks. What I tried to show you is that it may be useful to use quantum mechanics for building computers, that it's not easy to do that or to realize, to build such machines. There are a number of possible obstacles. Scaling is difficult, but what I try to show you is basically how some of these obstacles may be overcome in the future. And I would like to thank you for your attention.
Thank you very much. So are there questions? Yes? Can you try just to speak loud?
Well, that depends on the application. I mean, I think entanglement as such is not important, but in order to build a quantum computer which is more powerful than a classical computer, you have to be able to implement entangling gates. And these entangling gates, they can generate entanglement, but say whether you have entanglement in the system depends on the actual algorithm and on the input information that you need. And I can't give you any reason why having entanglement present should be important. Many people see that differently, but so you have to be able to create entanglement, but the entanglement itself is not relevant unless it's part of the algorithm that you're implementing.
Have you tried applying non-periodic pulses or quasi-periodic pulses to the excitations?
What do you mean with quasi? You mean not?
Instead of having periodic.
Oh, for dynamical decoupling?
Yes, yes.
Sure, yes. I mean, there is, for instance, a dynamical decoupling sequence called UDD, which has non-equal spacing, which has some advantages for some applications, but it also has disadvantages. And of course, I would say in principle, there is no reason to use a periodic sequence, with the main argument that it's always possible, instead of repeating the same cycle twice or 1,000 times, there is always a better cycle that you can append. So it's basically the reason we do use periodic sequences is because we're lazy. Because if you want, say, if you need, the basic requirement for preserving the information, say, for a second, means you have to apply 10,000 pulses maybe. That's the limitation. The pulses cannot be spaced too far apart because otherwise the environment changes and you won't get the information back. Now, how to choose those 10,000 pulses in optimal way, I'm almost sure that the optimal solution is non-periodic. But finding that solution is difficult. But generally, I mean, I showed relatively short sequences. We've also tried longers, and there is some improvement, but the improvement gets smaller. And so at some point, the effort is not worth it anymore. There are also some reasons not to do that. Maybe we can discuss that later.
Two questions. First, how many qubits can really be handled nowadays?
That depends very much on the actual system. The largest number of qubits that have been implemented in a in a general purpose quantum computer, I think is 12. There have been some, I think in the case of trapped ions, they went to 13 qubits and created a superposition state, but they did not implement the quantum algorithm. I showed you one example where we went up to 7,000 qubits, but this was not a general purpose quantum computer, it was a quantum simulator, which means you don't have access to the individual qubits, so you cannot implement arbitrary algorithms. Is that sufficient for an answer?
The other point is you said, okay, we have to proceed to the more fundamental description, which is quantum mechanics, but actually the most fundamental is rather quantum field theory, which has more flexibility, like creating, annihilating particles and so on. So can you imagine that sometime in the future also that would be relevant for this context?
That is, would be an interesting direction, yes. But I say at the moment I can't see what you would gain from that, but I certainly didn't think about that so far. So maybe you have the idea how to do that. Are you from quantum field theory? Okay. Yeah, so maybe it would be great if you can give us a motivation to do that. I mean, it should be possible if you use a more general theory, then you should be able to find an application which you cannot do without.
More questions? We thank Professor Suter again.